Ever wondered why sugar dissolves in your tea but oil doesn't mix with water? This is not mere kitchen science, but a captivating concept in chemistry known as solubility and distribution phenomenon. It's a fundamental principle that governs how substances interact with each other, and it's everywhere around us. From the food we eat to the medicine we take, solubility plays a critical role in our everyday lives. The phenomenon is based on the simple principle that like dissolves like. In other words, polar substances dissolve in polar solvents, and non-polar substances dissolve in non-polar solvents. But as we delve deeper, we'll find it's not just about being like or unlike. Factors such as temperature, pressure, and pH can influence solubility, and these interactions can be harnessed to our benefit in various fields. In the next scene, dive deeper into understanding solute-solvent interactions. What exactly happens when a solute interacts with a solvent? This question takes us into the fascinating world of solute-solvent interactions. When a solute and a solvent come together, they form a solution. But the process behind this is fascinating. Imagine you're at a party. You're more likely to mingle with people who share your interests, right? The same concept applies here. Molecules of similar types tend to mingle together, a principle known as like dissolves like. Polar solutes with positive and negative ends love to dissolve in polar solvents like water. On the other hand, non-polar solutes, those without charged ends, are more likely to dissolve in non-polar solvents like oil. In essence, solute-solvent interactions depend on the nature of the solute and the solvent. These interactions play a crucial role in the solubility of a substance. Now that you understand the basics of solute-solvent interactions, let's move on to defining solubility. What does solubility really mean? Let's break it down. By definition, solubility is the maximum amount of a substance, known as a solute, that can dissolve in a specific volume of solvent at a given temperature. It's all about how well things mix together. But it's not just a one-size-fits-all term. We have two types of solubility: intrinsic and saturation. Intrinsic solubility refers to the inherent ability of a solute to dissolve in a solvent without any external influences. Think of it as the natural tendency of a solute to mix with a solvent. On the other hand, saturation solubility refers to the maximum concentration of a solute that can dissolve in a solvent at a specific temperature, beyond which no more solute can be accommodated. It's like trying to add more sugar to a fully saturated cup of tea. With a clear understanding of solubility, it's time to explore how different states of matter interact with each other. Does gas dissolve in water? What about oil or sand? These are questions that might have popped into your mind at some point. And in this scene, we'll unravel the mystery of how gases, liquids, and solids dissolve in liquids. First up, gases. Ever wondered why your soda fizzes when you open it? That's because carbon dioxide gas is dissolved in it under pressure. When it comes to gases dissolving in liquids, the solubility increases with an increase in pressure and decreases with an increase in temperature. This is why your soda goes flat if left open. The gas escapes as the pressure decreases. Now, let's talk about liquids in liquids. Not all liquids mix. Ever tried mixing oil and water? They separate, don't they? This happens because oil is non-polar while water is polar, like dissolves like. Polar substances tend to dissolve in polar solvents and non-polar substances dissolve in non-polar solvents. So, oil being non-polar will dissolve in a non-polar solvent like hexane, but not in polar water. Finally, let's discuss solids in liquids. The solubility of a solid in a liquid is largely dependent on temperature. Think about making a cup of hot chocolate. The cocoa dissolves better in hot milk than in cold. As temperature increases, the kinetic energy of the molecules increases, causing more collisions between the solute and solvent molecules, and hence, more dissolving. But there's a catch. Not all solids follow this rule. Some solids, like salt, are almost unaffected by temperature changes, and some, like cerium sulfate, are less soluble in hot water. This is due to the complex interplay of factors such as the nature of the solid, the solvent used, and the specific interactions between them. Knowing how different substances dissolve in liquids, Let's look at the factors that influence this process. This understanding forms the basis of many everyday phenomena and scientific applications. From brewing your morning coffee to developing life-saving drugs, the solubility of gases, liquids, and solids in liquids plays a crucial role. Why does salt dissolve faster in hot water than in cold water? This question might seem simple, but the answer lies in a fascinating area of chemistry: the factors that affect solubility. Solubility is the maximum amount of a substance that can dissolve in a certain amount of solvent under specific conditions. Now, these conditions are where the factors affecting solubility come into play. Let's look at temperature, pressure, and the nature of the solute and solvent. First up is temperature. Picture a cup of hot tea. You add sugar and stir. It dissolves quickly. But if you try to dissolve the same amount of sugar in a cold glass of iced tea, it takes much longer. This is because solubility generally increases with temperature. As the temperature rises, the kinetic energy of the water molecules increases, making it easier for them to break apart the solute and integrate it into the solution. Next, we have pressure. The solubility of gases in liquids is directly proportional to the pressure of the gas above the liquid. This is known as Henry's law. So, if you increase the pressure, more gas dissolves. This is why when you open a can of soda, the decrease in pressure causes the gas to come out of the solution, creating those bubbles we all know and love. Finally, the nature of the solute and solvent also plays a significant role. We've all heard the phrase, like dissolves like. This means polar solvents, like water, are good at dissolving polar solutes like sugar, but non-polar solvents like oil are better at dissolving non-polar solutes like fat. So, next time you're making a cup of tea or opening a soda, remember the factors that affect solubility. It's not just about mixing things together, it's about temperature, pressure, and the nature of what you're mixing. Understanding these factors, let's now delve into the solubility of weak electrolytes. Ever wondered why weak electrolytes don't fully ionize in a solution? Well, let's unravel the mystery. Weak electrolytes are substances that partially ionize in solution, forming a balance between the unionized molecules and the ions produced. This partial ionization is due to the weak intermolecular forces between the ions and the solvent. When a weak electrolyte dissolves in water, only a small fraction breaks up into ions, while the majority remains as unionized molecules. Now, you might ask, how does pH and solvents influence this? Well, pH can impact the degree of ionization. For instance, a weak acid or base may ionize more at a certain pH level, affecting its solubility. On the other hand, the type of solvent also plays a crucial role. Polar solvents like water can stabilize ions, increasing the solubility of weak electrolytes. Having explored the solubility of weak electrolytes, let's conclude with the combined effect of pH and solvents. What happens when you change the pH of a solution or use a different solvent? Well, these two factors, pH and solvent, can significantly influence the solubility of a substance. Let's dive deeper into this fascinating concept. In an aqueous solution, the pH can alter the solubility of substances, especially weak electrolytes. This is because pH affects the ionization of these substances. For instance, acidic substances tend to be more soluble in alkaline solutions, while basic substances show higher solubility in acidic solutions. This is due to the neutralization reaction between the acid and the base, which aids in the dissolution process. Now let's talk about solvents. Solvents are not all the same, and the choice of solvent can have a profound impact on solubility. This happens because different solvents have different abilities to break the intermolecular bonds in the solute. The rule of thumb here is, like dissolves like. Polar solvents, like water, are good at dissolving polar and ionic solutes, while non-polar solvents, such as oil, are better at dissolving non-polar solutes. But what if we combine the effect of pH and the solvent? The result is a synergistic effect that can significantly impact solubility. For example, changing the pH can make a solute more or less polar, which in turn affects its solubility in a particular solvent. This brings us to the concept of the solubility parameter. This parameter is a numerical value that gives us an idea of a substance's polarity. It is a useful tool in predicting how changes in pH and solvent might affect solubility. So, if you know the solubility parameters of your solute and solvent, you can make an educated guess about how solubility will change under different conditions. In conclusion, both pH and the type of solvent can dramatically alter the solubility of a substance. Understanding these effects allows us to control solubility, which is crucial in many fields, from pharmaceuticals to food science. Now you know how pH and solvents can drastically affect a substance's solubility. So, why does all this matter? Well, understanding solubility and distribution phenomena isn't just for the chemistry buffs. It's a crucial cog in the wheel of science, impacting everything from medicine to environmental science. Today, we've delved into the intricate world of solute-solvent interactions, understood the definition of solubility, and unpacked the concept of intrinsic and saturation solubility. We've explored how gases, liquids, and solids dissolve in liquids and the factors that affect their solubility. We've also touched on the solubility of weak electrolytes and how pH and solvents can influence solubility. All these components help us to predict and control how substances interact in the real world. So, the next time you're sipping on your fizzy drink or taking a pill for a headache, remember the science behind it. Subscribe for more because you won't find me later. Stay curious, keep learning,